This video is about the mole, molar mass, and some calculations associated with the mole. All right, so first thing I want to talk about is take your periodic table. You can look at your periodic table and determine the mass that a particular molecule is going to have by adding up the masses of the individual atoms from the table. So if I look at something like carbon and it says 12.011, that would be the weighted average of one carbon atom. Okay, well, what if it wasn't just an element, but it was a molecule? Like in this case here, we've got a water molecule. So a water molecule consists of two hydrogens and one oxygen. So I've got my mass of a hydrogen, and then I've got my mass of an oxygen, multiplying that by 1 because there's only one of them here, multiplying this one by 2 because there are 2 of them there. And when I do this, I end up with this value here. So the mass of a single water molecule is 18.0153 AMU. So you're literally just adding the masses together based off of how many of each of those atoms are in the molecule. So here's our 12.011 mass of carbon, one of those guys, and the mass of an oxygen times 2 because carbon dioxide has 2 of them, and 44.0098 is the mass of a single carbon dioxide molecule. We can keep going with this. This is benzene. There are 6 carbons and there are 6 hydrogens. And if I do the math on that, I end up with this 78 value. And then here's an ethanol molecule. And so there's 2 carbons and 6 hydrogens and a single oxygen. So I get this mass of 46.0691 for a single single molecule of ethanol. Okay, but as I'm saying here, all seriousness, this is not super useful. We do not have the ability to go get one of these. I gave you a scale in your lab kits, and you could not mass out a single molecule of ethanol or benzene or CO2 or water. It just would not be possible. So when we're dealing with real world amounts, we're going to need to change this a little bit. And so the way that we're going to change this is we're going to talk about a value called the mole. The mole has traditionally been something that confused students, but it shouldn't. The mole is just a word for a number. That's it. Just like the word 6 describes 1, 2, 3, 4, 5, 6 objects. SIX, they're all the same thing. So dozen is easy, means 12. Well, what does that mean to you when you say dozen? It means that. Maybe it means a dozen eggs. Maybe it means a dozen donuts. But the word dozen has a meaning in your head. You can visualize an amount. So we need something bigger than 6 or 12. We need something much, much bigger because the atoms themselves are very small. They are too small to be worked with on an individual basis. So what we're going to need to do is we're going to have to gather a bunch of them together to have anything that's worthwhile. If you somehow were to put 1 billion water molecules in your hand and then throw it at your face, you wouldn't feel anything. You wouldn't know that you threw it, and you wouldn't know that you got hit with it because 1 billion is not enough for your body to even register that you were hit with it. And I know 1 billion sounds like a lot, and in terms of money it is, but in terms of atoms, it's absolutely nothing. You are currently, right now, being pummeled by billions and billions and trillions and quadrillions of atoms pounding into your face, into your eyeballs. You don't even notice it. Okay, so a person named Lorenzo Romano Almeida Carlo Avogadro did some work with gases, and we're actually going to discuss him more in detail towards the end of the course. And because he did this work with gases, the people who came up with the number that we're going to talk about decided to name it after him, because without his work, they would not have been able to accomplish what they did. So there's a Jurassic Park line talking about standing on the shoulders of giants to take the next step in understanding something in the scientific process. And so the reason that Avogadro gets this number named after him is because the people who did this realized his work is important enough to name it after. Okay, so we're fine with numbers like 12 maybe even a baker's dozen, which is 13. It's 13, so the baker can eat one and then give a dozen to everybody else. A gross is a number equal to 144. You might not use the word gross very often. I remember buying a gross of pencils. It was this big box with 144 pencils in it. It fits nicely inside of a container. Or a ream of paper, like copier paper. The ream means 500 pieces of paper, or 500, and in that case, it's going to mean paper. So the mole is just a word for a number, but that's the number. So the problem is the number is stupid big. So how big is it? So we're talking about thousands, millions, billions, trillions, quadrillions, thousands, millions, billions, trillions, quadrillions, pentillions, hexillion. Oh yeah, hex. So that's 6 illions. So that's a lot. That would be a number like this. We're talking about 602 hexillion. This number is too large for us to comprehend. On a mental level, it just doesn't compute. So if the entire world's population were to count 1 mole of gold, it would take us 8 million years. If every single person on the planet was counting 1 gold atom, and we were working 48-hour weeks with around the current population, again, 8 million years. So we're obviously not going to be counting atoms. We would like to be able to count them, but we're going to count them in a different way. So other examples of how big this is a mole of penny. You'd pay off all the expenses of the United States for the next billion years. A mole of marshmallows, the larger ones, would cover the United States 600 miles deep in marshmallows, just straight up a tower of marshmallows. Space is 100 miles away, nominally. So we're talking 500 miles into space, outside the atmosphere, we got this tower of marshmallows coming out. A mole of German shepherds would be bigger than Earth, so be more massive than Earth. So again, we need a big number like this because the atoms themselves are so utterly tiny. If you were talking about getting some salt, you wouldn't ask to get like, I need 8 crystals of salt. That's not enough salt probably to do what it is you're doing. Even in like a quarter teaspoon, there's a heck of a lot more than 8. So we need to make sure that we're using a number big enough to allow us to have something to work with. An example is 1 mole of water molecules is 18 milliliters. And so you guys have a graduated cylinder, go grab it. I'll go ahead and pause the video, go grab it, a graduated cylinder, and look at it and see how many milliliters 18 is. That's not very much. That's like a mouthful, maybe a mouthful of water. And you're talking about this huge amount of water molecules in just that. So how many water molecules are in a full glass? How many water molecules are in a bathtub? How many water molecules pummel you when you're in the shower? How many molecules are in the Columbia River right now? I mean, the number is enormous. So we're not going to be counting anything. Instead, we are going to be massing these things out. And so the kind of the cool thing about the periodic table and what we talked about up here, these values here, with the water molecule being 18.0153, we're going to come down to this table. Well, this little graphic here. And so I've got my water molecule mass and my oxygen mass, and I'm ×2 and ×1. And here, that number is exactly the same. Difference is the most important thing, the unit. So now what I'm talking about is instead of it being 18.015 AMUs, which is phenomenally small amount, I've got 18.0153 grams. So that's significantly larger. But the caveat is my 18.0153 grams of water molecules, I'll have that many grams if I have 1 mole of water molecules. So if I've got the 6.02 times 10 to the 23rd water molecules, I've got this 18 grams of water. That's the super awesome abbreviation for MOLE. You just drop the E. I don't know why there's not a better abbreviation for mole, but that's all it is. All right. So what I want to be stuck in your head, the most important thing about this for me is for you to understand when you're going to get something, so in a lab, if it says to go get, 2.5 grams of something, I want you to be thinking about 2.5, let's say it's, I don't know, calcium carbonate, so powdered chalk. I want you to think about 2.5 grams of them. I want 2.5 grams of calcium carbonates. I don't want you to say 2.5 grams of it. It isn't the thing. There isn't, when I'm going to get this calcium carbonate, it isn't an it, it's a whole bunch of it's, a lot of things. So when we're thinking about getting something, I want us to think about getting a whole bunch of those things. That's very important conceptually to realize. There isn't an it, there's a them. All right, so why do I care about that? Why do I care about you understanding that when you're going to get stuff, that you're getting a whole bunch of individual objects as opposed to a chunk of object? It's because chemistry works in the same way that building this big wheel would. All right, so big wheels, super fun. Sadly, they only hold 125 pounds, so they're useless to me now. But if you were to build one of these, what would you need? Well, you'd need a set of handlebars. You need 2 streamers. You need 2 small wheels. You'd need a back seat. You need a frame. You need a fork. You need 2 pedals. You need a spindle. You need a big wheel, and you need some bolts. 2 bolts and 2 nuts to go along with those bolts. What I didn't say was anything about weight or mass. I did not say I need 1.75 pounds of big wheel. Why? Because I can count to 1. I can go get that object and get 1 of those big wheels. But if I did use the mass part, well, if I knew how much what the mass of a big wheel is, then I could say, okay, well, the mass of that is the mass of 1 wheel, so I got 1 wheel. So this is important to us because when I'm talking about a chemical reaction, like hydrogens and oxygens going together to make water molecules, if I take 2 H2s and 1 O2, I will make 2 water molecules. Same situation. I didn't say anything about mass. It takes 2 of these and 1 of these to make 2 of those. And that's how all chemical reactions work. I have some of these and some of those, and I make some of this in the same way that you build anything. When you put those things together, you need X number of objects of this. If you're going to build an IKEA bookshelf, you need like 4 shelves. You need a frame. You need, I don't know what those little screw things are that you put them in, and then toolless casters. I think maybe they're called casters to put the pieces together. But at no point does it say anything about mass. You need this number of these objects or it just doesn't work. So I need us to be thinking about the fact that instead of getting stuff, we're getting a bunch of little things put together to make a certain amount of stuff. Okay, yeah, we just talked about that. All right, so the next thing we're going to talk about are some mole calculations. We're going to run through these because they can be mildly useful. There's going to be a better way to do this later on for us, but I want us to look at this. So if I had 2 moles of iron, well, how much iron would I have? Okay, so the way that I do this calculation, I use the railroad track, and I want to change my moles of iron, and I want to turn my moles of iron into grams of iron. Okay, so where did this number come from? And why is this fraction okay? That's the number off the periodic table, because on the periodic table, all those mass numbers that are underneath the symbols and the names, if I have that many in grams, that's telling me what my gram value would be if I had a mole of those. So then if I just multiply this by 2, I get my 107 or 111.7 grams of iron. So if I had 2 moles of iron, I would have this mass of iron. Well, what if I had a mass of iron? In this case, I had a mass of silicon. So I've got 50 grams of silicon. How much silicon do I have in terms of moles? All right, so this number came off the periodic table. And when I do these fractions, it's always going to be 1 mole to whatever the number is off the periodic table, no matter what my situation is. If I'm looking for a number off the periodic table, even if it's a molecule, I'm going to be pulling those masses off and then setting it equal to 1 mole. because that's how it works with the table. So then I do the math on this and I end up with 1.78 moles of silicon, which makes sense because it's about 28 grams is equal to 1 mole if I'm talking about silicon, and I have 50 grams. So I've got more than 1, but I have less than 2 moles. What about something a little silly about how many atoms are found in a 7-gram gold ring? All right, so I've got gold, it's 7 grams. This, again, number came off the periodic table, set to 1 mole, so that way the grams cancel out. And then I'm going to take my mole value, and 1 mole of anything is equal to that many objects of whatever that thing is. And so I can cancel the moles out with the atoms and do the math, and I end up with this huge number. Again, not super useful, but kind of interesting to realize you have that many atoms in a particular ring. All right, so again, what if we're talking about molecules? Okay, so this is 2.8 grams of table salt. All right, I want to turn that into a number of moles of table salt. This number is nowhere on the table. So where did this number come from? Well, it's 22.9898 plus 35.453 added up to give me, well, in this case, I truncated it, but it's about 44 grams. That's it. So like we did a little bit earlier, where I showed you in that table, my masses are equivalent to mass off the periodic table multiplied by whatever its coefficient or whatever its subscript is, added to the other molecules, multiplied by their subscript, and 44. All right, so what we're doing when we mass something out, we're actually counting them. So if we look at this atom one here, you take a ring and you put this ring on a scale, and I find out it's 7 grams. Well, how many atoms are there? Well, again, we use this ratio of grams to moles and then go from moles into atoms. We just counted the number of atoms in that gold ring without actually counting them. So it is totally possible to count something without actually counting them if you know how much what the mass of one of them is, and then you divide through by that number. So you guys did the penny lab, and the pre-82 pennies had a mass of around 3 grams. So if somebody came in and said, all right, I got this bag of pennies, and this bag of pennies has a mass of 396 grams. Great, okay, so I got this bag of penny with 396 grams. How many pennies are there? Well, if I divide through by 3 grams is equal to 1 penny, what is that? 132 pennies. So the grams cancel out, and now I know how many pennies I have in this bag of 396 grams. And that's what we're doing. I'll give you another example. My mom, after I left high school, my mom moved my brothers and sisters to Astoria, and they used to go to the Seaside Arcade and win tickets. And they realized real quick after a while that that you could spend all day there and spend like 20, 30, 40 bucks and still walk away with like 2 Jolly Ranchers and a pencil. So what they decided to do was keep their tickets. So my mom had this like waist size high owl made out of glass that was hollow. And so when they'd come back from the arcade, they'd throw their tickets in there. And over the course of years, their friends decided to do the same thing. So the owl would fill up, my mom would throw it into a trash bag, and they just kept filling the owl up. And when my brother graduated from high school, they decided to turn all the tickets in. So they showed up with 9.5 bags of tickets. And these are large tickets, or large bags, like the 33.5 gallon full-size trash can bags. And the poor kid that was there, he did not count all those tickets. What he did is he took the tickets, handfuls of tickets, and put them on a scale, and then read what the scale said. So they knew how many tickets there were per X number of ounces. And so he would look at this and say, okay, this has a mass of, or this thing's weight is, it doesn't really matter, 68 ounces. And so he would look at the table and say, that's X number of tickets. It's like 2,408 tickets. And so they kept going through this until all of the bags were empty and all the tickets were accounted for. And so they never actually counted a single ticket, but they counted all of the tickets based off of their mass. And that's how we mass things out in this class. And we need to mass things out in the same way that kid had to mass out those tickets. They couldn't just walk up with the bags and say, we've got 9.5 bags. Give us the paint gun and the giant giraffe. He had to know how many actual tickets were there, because that's how it works. It's 47,000 tickets for the paintball gun or whatever it was. And so that's how it works in chemistry. In chemistry, you need to have 2 H2s to go with 1 O2 to make 2 H2Os. So you need specific numbers of objects. I need 1 big wheel. I need 2 small wheels. It matters. I can't have 1 small wheel and 2 big wheels. That does not work. So I need to be able to count them so I know exactly how many of them, each of them I have, and then I can put them together in ratios that make sense. And that's it. All right. Thank you.